Okay, so let's look at the solutions to quiz 3. So, excuse me. This first part of the problem talks about the amount of atomic sites with vacancies given a temperature and given an activation energy. So that should tell you that we're dealing with the Arrhenius relationship that we have back here. This Arrhenius relationship. The fact that the problem is asking you for the fraction of atomic sites. That's saying, well, fraction is the not an absolute number. So we're actually looking for the number of vacancies divided by the total number of sites. And that makes it a little bit easier because we don't have to figure out the total number of sites. And if you remember the practice problem that we saw in class, one of the challenges was getting the absolute value of n. So if we talk about site fractions, this simplifies the problem significantly. And that gives us exp negative qv over kt. So that's the equation we have. We're solving for this. We have qv, and that's in millielectron volt. So that's 300 times 10 to the minus 3 electron volt, where milli is the same as millimeter. 1 times 10 to the minus 3 meter, 1 times 10 to the minus 3 electron volt. So that is going to go in for Q. T is in Kelvin, right? That's 500. Which means that we need to pick the Boltzmann constant in the proper units. And we have it here. K, here we have it in terms of joule per atom per K, or Kelvin. And here we have it in electron volt per atom per Kelvin. So K is equal to 8.62 times 10 to the minus 5 eV per atom K. And substituting in for K, T, and Q, we get 9.49 times 10 to the minus 4. Okay, next question. Given the lattice parameter, and given that we have an FCC crystal, determine the angle for diffraction coming from the 111 planes, given the X-ray wavelength. Okay, so that says we're going to be using the equation for diffraction, and we saw that last time was this, that's Bragg's law, n lambda equals 2d sine theta, and that d, that's the d spacing. So that d spacing comes from the HKL planes, and that is this equation. So we have d, HKL, and these are the 111 planes, 111 is equal to a divided by square root of 1 plus 1 plus 1. A squared of 3. In this case, A is 3 angstrom. So put in 3 over square root 3 is equal to the square root of 3 angstrom. Now I could have changed the units to something else, but we don't have to as long as the units all cancel out, and we're going to be going to n lambda equals 2d sine theta, and if that d is in angstrom, as long as our lambda is also in angstrom, we're okay. And fortunately, whoever wrote this problem was planning ahead and decided to give you your lambda in angstrom as well. So we have lambda as 1.5 angstrom. We have d as square root of 3 angstrom. 2 is just a value. We're solving for sine theta. Last question is, what is n? So n is essentially the integral number of path lengths of wavelengths that map in the diffraction pattern. It's a constant. It's an integer. And I told you last time that we can get diffraction from n equals 1, 2, 3, 4, 5, and so on, but really the highest intensity is going to be coming from n equals 1. We talked about this in class, so we're going to use 1. And substituting in all of these and then taking the arc sine, we get theta is equal to 25.66 degrees. Okay, now the last problem is a problem in which I'm asking you to identify the relationship between the Burgers vector, the line vector, and the nature of the dislocation. So you learned in class that the line vector always runs tangential to the dislocation line, and the Burgers vector is always fixed B. So then the question is, where are we seeing pure edge to draw a circle around? Well, we see pure edge when the Burgers vector and the line vector are at 90 degrees, which would occur right here. The next question is, draw a square around the region where we see pure screw. So that's where the Burgers vector and the line vector are parallel. That's here. So this type of problem is the type of problem I like on exams, because this simple problem itself shows that you understand the meaning of the line vector, the meaning of the Burgers vector, the relationship between the two, and the fact that you can get mixed edge and screw components in this whole region here. And this type of simple problem is also relatively easy to grade because you have 2 points, and people that are taking the time to study, if you study this subject prior to the exam, it's relatively simple for you to answer it. I mean, there's no chance for a calculator error, there's no chance for excuse me, really any mess ups, except lack of understanding. So these type of problems I like for exams a great deal. So let me zoom out here. Oops. This is the solutions to quiz number 3.